Greetings from SJBIT Institute of Technology. As we have seen in the previous session, module 3 second part, which is about the radiation mechanism, antenna basics. Then we'll see about the remaining parameter definitions in this module or in this session. As we have seen about different types of antennas and the radiation pattern. This is about the radiation pattern in 3D, in three-dimensional form. So you will have both in theta direction and phi direction, which is spherical coordinate system is the one which we follow here. The spherical coordinates are r, theta and phi. So as it is difficult to interpret, we'll go with the 2D pattern. Suppose something like an apple, if you cut in one direction, it can be seen like if I see from one end, I can be able to see like a elevation, like when phi equals to 0, we call it as a elevation plane, E plane. Then if I look in from the top, you can see like a circle. It is nothing but in azimuthal plane, which is when theta is constant 90 degrees. Phi where phi is varying and here theta is varying. Based on this, you will have E plane and H plane. Okay, then any radiation pattern can be represented in 2 dimension as in either in E plane or in H plane. So the principal patterns in 2D pattern are linearly polarized, and of a linearly polarized antenna is measured in 2 planes. One is E plane, another one is H plane. So E plane is the one, it is a plane parallel to electric field vector containing the direction of maximum radiation. Whereas H plane is a one parallel to H vector, which is orthogonal to electric plane and contains the maximum direction. So this is the one which you can observe from an aperture antenna. It is a horn antenna. The radiation pattern is unidirectional, directional antenna, radiating only in one particular direction. One can notice here this is a H plane radiation pattern. If you look from the top, then yellow color one. If you look from the top, then if you cut from one side, then it can be seen like this. Then it is a E plane radiation pattern. Vertically, E plane radiation pattern. Horizontally, you will have H plane radiation pattern. Okay, in usually in one direction will vary only theta, in another direction will vary only phi. If we vary only phi, then you will result with horizontal plane, that is H plane. If you vary only theta, then you result with electric plane, E plane, or this one electric plane or E plane perpendicular to H plane vertically, horizontal and vertical. Okay, then this isotropic antenna already we have discussed, radiates, hypothetical antenna radiates uniformly in all directions. So directional antenna, as I have told you, which is nothing but radiating in only radiating or receiving power in only one particular direction, not in all the radiation. This is an example of directional radiation pattern. Next is omnidirectional radiation pattern. As I have told you, it has a directional radiation pattern in one direction and non-directional radiation pattern in another direction. So that is the case of omnidirectional radiation pattern. You can observe here like a donut shape in vertical plane. If you cut, you will get like a circle in case of H plane. So this is the best example of omnidirectional radiation pattern. Now we'll define about the parameters. First parameter, which is nothing but the radiation pattern. It is a mathematical or graphical representation of the radiation properties of an antenna. That properties could be, it can be either amplitude or phase or polarization or etc. It can be any of this, and all these will be measured in terms of or as a function of angular space coordinates. So that is theta and phi, E and H. So coming to first one, amplitude radiation pattern. Majorly we'll be focusing on amplitude radiation pattern. amplitude pattern will have again a field pattern and power pattern classified into. Field pattern indicating you are plotting the electric field or magnetic field intensity on a linear scale, whereas power pattern you are plotting the power, which is nothing but electric field square or magnetic field square on a linear scale or a decibel scale. Any one of that could be possible. So if I usually sometimes they can say that the normalized pattern indicating the electric field intensity, if you divide with its maximum value, then it results with electric field intensity normalized one. Usually it is a dimensionless. Similarly, power pattern, normalized power pattern indicating power density, if you divide with its maximum power density, then results with a dimensionless quantity, which is a normalized power. Units are watts per meter square, whereas normalized power won't have any units. Normalized power pattern. This is an example of polar pattern of a radiation pattern. You can observe with respect to the angle we will be plotting here. So here you can notice that this is a major axis, this is a major lobe, means we have a radiation pattern measured in terms of angles. So there comes the picture of lobes. So here all these are the side lobes, and the back lobe exactly perpendicular to major lobe is a back lobe. The lobes which are adjacent to the major lobe are side lobes, whereas the other all other lobes are called as a minor lobes. And we know major lobe, minor lobe, back lobe, all these things, what does that represent? The electric field or magnetic field, or it could be power, normalized or normalized power or normal power variation with respect to angular parameters. And two more parameters that we can define here is half power beam width and first null beam width. Half power beam width, name itself indicates if this is a power pattern, if this is the maximum power, normalized power pattern, if I consider this is 1, and if I measure the power at this point, this should be 0.5, half, where the power becomes half. Name itself indicates it is the angular separation between the points where the power becomes half of its maximum value. Similarly, next, first null beam width. Null indicating where the radiation has become 0. These are the points where the radiation is becoming 0. Even this point, even this point, even at this point, even at this point. But if I consider the first null, first time adjacent to major lobe, where it is getting the 0 value of field intensity as 0, that we'll consider as a first null. The angular separation between these two is called as a first null beam width. Okay. So usually the relation between first null beam width and FNBW and HPBW is FNBW is 2 times of HPBW, twice it will be. That is on a polar scale. The same thing can be represented in linear scale also. So this is the one replica, usually, as you know that this is the horizon, replica of that you can observe. So half power beam width where power becoming half, first null beam width where the radiation becomes 0 first time, and these are the side lobes, minor lobes. This is known as a major lobe, radiation intensity where it is maximum, and the last one exactly opposite to major lobe is a back lobe. And half power beam width, first null beam width, already I have told, where it is the angular separation between the points where the power becomes half. Relation also already I have told. Then coming to next parameter to define about beam area, beam efficiency, we need to know about few more parameters called as a radian, steradian, and the other radian, steradian, and spherical coordinate system. So radian, already we know that it is a plane angle measurement. If we consider a circle with its vertex at the center of radius r, then if you make an arc of length radius as arc, the angle which is measured over here is represented as 1 radian. In a circle, if you observe like this, you will have circumference of the circle, as we know, which is 2 pi r. one arc length is r, total if I want to get 2 pi r. Suppose how many radians that we have if I want to measure means total circumference divided by r. If you calculate, you'll get to know how many radians that you will have. So which is 2 pi r by r will give you 2 pi radians, indicating in one circle you'll have 2 pi radians. In the similar manner, we have a steradian, which is defined for a spherical coordinate system, spherical sphere. In a sphere, it is a measure of a solid angle. It is defined as with its vertex at the center of the sphere of radius r, that is subtended by a spherical surface area which is equal to the area of a square with each side as having a length as r square, that you will get. Then the area of sphere, as we know, if you consider the angle, that one angle is called as a steradian. As we know, area of a sphere is 4 pi r square. If I want to get how many steradians that you have in one sphere means total area divided by r square gives you 4 pi steradians. Or the same thing you can prove by integration. Here we have defined few more parameters called as d omega, which is known as a beam solid angle, which is dA by r square. dA is incremental area that you can observe from this graph. Consider this as a spherical coordinate system relating a solid angle and the incremental angle. The smallest area, if I want to consider, by considering r, d phi and d theta, one can notice the area is considered as r square into sin theta d phi. If I represent sin theta d phi as d omega solid angle, then this gives you r square into d omega. So here d omega is solid angle, dA is incremental or infinitesimal area on the surface of the sphere. So on the surface of the sphere, infinitesimal area is r square into d omega. D omega is solid angle. It can be represented either in radians or in square degrees. So if I convert the 4 pi steradians into degrees, then you will get 41253 square degrees. That is during the conversion process. So now we'll define about one more parameter known as a beam area or beam solid angle. Symbol is omega A of an antenna. It is defined as an integral of normalized power pattern over the sphere. Normalized power pattern, which is Pn of theta comma phi into d omega over the sphere, which I need to integrate it. So when you are integrating over the sphere, if they didn't give, you need to assume theta is varied between 0 to pi, whereas phi is varied between 0 to 2 pi. Phi indicating in H plane, whereas theta indicating in E plane. E plane 180 degrees, H plane 360 degrees. It is an omnidirectional radiation pattern, omnidirectional system. So beam efficiency, if I define, it is a total beam area which will have majorly consisting of major lobe and minor lobe beam area. So major lobe and minor lobe. So beam efficiency is defined as major lobe beam area to total beam area, which is known as beam efficiency, whereas minor lobe to total beam area we call it as a stray factor, together obviously which should be equal to unity. Next parameter which we define is radiation intensity, which is defined as U, the symbol as U. It is defined as the power radiated by an antenna per unit solid angle. You can find out radiated power if you know the radiation intensity by integrating over the sphere. So you can evaluate for an isotropic antenna, which gives you U0 value, the radiation intensity as 4 pi P radiated by 4 pi. Another formula for radiation intensity is E square by 2 eta into R square. Then another parameter which we call it as a directivity. It is defined as the ratio of radiation intensity of a given antenna in a given direction to the radiation intensity which is averaged over all the directions, U by U0 or S by S0. or you can also express this as, because u naught is nothing but p radiated by 4 pi. By substituting that, you can also express this in this manner. If I want to maximize this, then you can maximize the parameter u as u max. Then you can also express that in terms of decibels. So here you can observe this is the average radiation pattern or radiation intensity of isotropic antenna. This is for directional antenna. In comparison with respect to this, we'll define the directivity. It is a comparative parameter actually. So you can either define in terms of radiation intensity or in terms of radiated power density. So, or you can also define the directivity in terms of omega A, beam area or beam solid angle. Omega A is a beam solid angle. It is inversely proportional. One can derive that. So this is an example for during the conversion process. You can have either it in either in degrees or in radians. Suppose if you know omega A in degrees, directly you can convert that into as 41253 or 41,000 divided by degrees. And if you know this is again another parameter. This is an example of considering an infinitesimal dipole, evaluating the radiation pattern from radiation pattern directivity. Then next we'll define about one more parameter called as a gain. So power gain, you have gain of an antenna which is defined as a ratio of means actually 4 pi into u divided by radiation intensity in a given direction to the net accepted power, not radiated power, whereas directivity is with respect to radiated power. That is the major difference. Actually it defines about how effectively the antenna is transforming the available power into the radiated power. Is there any losses or not? So if I relate gain and directivity, you can you can define one more parameter called as an efficiency. So how effectively the radiation has happened, you can measure through the gain parameter. Gain is equal to efficiency times directivity. So coming to the another one, which is nothing but the input impedance. If you know input impedance, which is input impedance is a complex quantity. You will have a real part and imaginary part. The real part, you will have a radiation loss and the ohmic loss. Actually this is the one which we need to be enhanced. Suppose if I know the radiation resistance, then you can evaluate from the input power, or if you know IA, you can evaluate I square R formula. So from that you can also relate an input impedance and efficiency formulas. So input power is nothing but radiated power and the loss power. Input power I square R, radiated power I square R only, but radiation resistance. Loss power I square R, R is loss resistance. From that radiated power you can calculate. From that efficiency, P radiated by P in, P radiated by P radiated plus loss. If I express, then you will get radiation resistance to total resistance. So you can evaluate the efficiency in two different ways. One is, if you know gain and directivity, efficiency is gain by directivity, and if you know radiation resistance and the input resistance, efficiency is radiation resistance to total resistance. Now coming to effective antenna vector length, effective length and the equivalent areas, then followed by few more parameters. Effective length is means if you consider wire antennas or such kind, linear or aperture antennas, total length whatever you make use cannot be effectively utilized for radiation into the free space. If I want to evaluate the effective length, which is defined as ratio of voltage to electric field intensity, incident voltage to induced EMF, induced voltage to incident electric field. Similarly, antenna equivalent areas, effective area, you can evaluate the effective area, means as you know that the total area can't be utilized effectively for radiation. Effective area can be evaluated by PT by 4 WI. So one can evaluate total power I square R formula. Then from that you can evaluate effective aperture of an antenna. So effective apertures which will not be same as the physical aperture. Physical aperture by means one can calculate the physical aperture based on the geometry. It cannot be same as effective aperture. One can define a parameter called as aperture efficiency, which is maximum effective area to the physical area. So next one, two more concepts that we have is about Friis transmission formula, or we also call it as a radar range equation. Friis is the one who had related the power radiated and power transmitted by the two antennas. This is transmitting antenna and this is receiving antenna, keeping a distance between these two as 2d square by lambda, satisfying the range equation, where d indicating the diameter of the antenna. And let us consider that we have an antenna which is transmitting initially as isotropic. Then the power density will be PT into efficiency ET divided by 4 pi r square. Then as it is a non-isotropic antenna, power density you can also evaluate with the gain, then PT GT by 4 pi r square. As it is receiving and with no losses, same means receiving antenna will, if it receives the total power, then you can equate the transmitted power to the received power. Considering the effective aperture in between, then you can relate the radiated power to the received power as efficiency ET into lambda square, lambda 4 pi r by lambda whole square, dt into gt, or you can also write it as gt into gr divided by 4 pi r by lambda whole square. Or this is the one, PR by PT is nothing but gt gr into lambda by 4 pi r whole square. So this is the one relating transmitting and receiving power of two antennas which are separated by a distance of 2d square by lambda. Next, the last concept what we have is field zones. So you have majorly the space which is surrounded by the antenna. It is divided into three regions. They are near field, Fresnel region, radiating near field, and radiating far field. So reactive field, near field region, it is the portion, the near field region which is immediately surrounding to the antenna, where the reactive field is predominating. For most of this, commonly we consider the distance as r, consider radiation distance that exists less than 0.62 into square root of d cube by lambda. Then that region is considered as a reactive near field region. Then for radiating near field region, we also call it as a Fresnel region. It is the boundary surrounded between 0.62 square root of d cube by lambda and less than 2d square by lambda. In between that, the region which is between these two boundaries, we call it as a near field, radiating near field region. We also call it as a Fresnel region. So if the antenna has a maximum overall dimension which is very small compared to the wavelength, this region usually may not exist. And last one, which is known as a far field region or Fraunhofer region, the region of the field of an antenna where the angular field distribution is essentially independent of the distance from the antenna. So the region which is commonly exist at a distance greater than 2d square by lambda from the antenna. D is the maximum aperture of an antenna. So majorly here you can observe, so this is a reacting near field region and radiating near field region and Fraunhofer region. The means less than R1 is when the distance is less than this, then it is a near field. When the boundary it is between greater than this and less than this, then it is near field region. Radiating near field greater than 2d square by lambda results in Fraunhofer region, that is far field region, where the fields are independent of distance from the antenna. Angular field distribution is essentially independent of the distance from the antenna. So with this, which we have completed all the parameter definitions of an antenna and module 3. Thank you.